Good afternoon. I'm Ted Hahn. I'm an independent SRE for hire, and this is my father, Mark. He's an enterprise DevOps consultant with Cyber Global. Cool. And this is our talk, Control Theory for SRE. So let's talk first about the history of control theory. All the way back to the age of steam, engines had a problem. You can control the power that is output by an engine by feeding it more fuel or less fuel. But that relationship is nonlinear, and more importantly, it's non-deterministically nonlinear. There's not a one-to-one ratio. There's not even a 2-to-1 ratio of coal fired into the boiler versus the amount of force it puts out.
We'll talk about the way that we've developed some of the algorithms that we use to try and control these processes that show emergent behavior, complex behavior. What can we use to do that? So back in the days of steam engines, we had this centrifugal governor that I'm sure you've all seen pictures of in old handbooks. And the way this works is it takes the existing system's speed, which is coming in on this crankshaft here, that then turns this cylinder, which causes these balls to rotate. As they rotate more, the weight pulls them out to the side. When they come out to the side, these little levers up here, they're kind of hard to see, push down this central white control rod. And in doing so, they close these two valves here, the white valves there, which let in less steam. With less steam into the steam engine, then the whole process slows down, and then this shaft slows down, and then the feedback continues as the balls move lower and the valve opens up more. And now we get a process that very smoothly, in an analog and smooth way, provides feedback and keeps the engine running at a constant speed. So this is very similar to the way that boat steering actually works with a helmsman at the tiller for the boat. Is they're gonna do the same sorts of things that happen with that centrifugal governor, but they're gonna do so manually. And they in the early 1900s, there were a lot of people looking at ways to automate ways to improve steering and automate the steering that's done by a human. So a guy named Elmer Sperry developed a control system for it. Elmer Sperry went on to found a company, Sperry Univac, if you remember that company. He was the Sperry for Sperry Univac. But his, if you read the Wikipedia article, it says that his ship steering mechanism was a PID-type controller, but it tended to use intuition rather than a mathematically based approach. And so I think when we look at the ways that a lot of systems are scaling today, there's a lot of intuitive scaling that goes on in our cloud-based systems. There's not a lot of mathematic-based systems. Mathematics, the PID controller, can be attributed to Nicholas Mirsky, who said here, and I think this quote is really important, that more accurate automated steering means that we can accomplish more, we can reduce the risk of manual control, and that's very important as the size of ships and so forth become much bigger and more complex. And I think when you look at our cloud systems today, they are becoming much bigger and more complex. And so we need to dig into something that does a much better job of describing the math and gives us an ability to scale without overshooting the scale that we need or undershooting, and responds pretty well to the existing inputs that are coming in. And that's where the mathematics of a PID controller arrive. PID, well.
Yeah. So a PID controller is named such for its 3 terms that are used in it. There is a proportional term, an integral term, and a derivative term. Each of these is expressed in an error value. Your PID controller takes as its input a set point, which is your target value, and the process variable, which is the measured state of your output. So what your system, what your system's current state is feeds back into the algorithm. Between the three, between those 3 terms, the proportional, integral, and derivative portion, you can gently home in on your target value, even as that target value moves. So the proportional term is very simple. It is just the error value itself. It is the amount that you are off from your target value. The integral component is a little more complex. It is the accumulated error over time. So with each iteration of your PID controller, the error value is accumulated, and that accumulator feeds in to your control state. And lastly, there is the derivative portion, which represents the current direction you have been steering, the current moving state of the system. This prevents overshoot by, taking the derivative, predicting into the future where you are currently, where the change in the error has been going. So let's talk about how you represent this in Prometheus. So each of the components are fairly simple in Prometheus. So you have your KP term is just we take the average here just because of the way that I have set up my controller. My control KP value, which is the coefficient that we use on top of the error, as well as the error itself. For the I component, we use the sum over time of our error. We don't use the sum of all time. You could. For this purposes, we're just using the sum over time of 10 minutes. In a real production system, that would probably be longer or shorter, depending on how fast your Prometheus iterates. And lastly, there is the D component derivative, which is the instantaneous delta, the time between, or the change between the last 2 points in time that Prometheus has measured, multiplied by the count over time to predict out as far as the I term is to calculate the window equal to the window length that we're using for our I term. Let's talk a little bit more about it. For our simulation, we simulate a moving vehicle, and that vehicle has a location. This location is our measured variable, the process variable. And that is, at each step of our iteration, at each step of our system, that is simply the previous location plus the velocity. Our velocity is controlled by our control variable, and this is itself just another iteration. Each step, the control variable is added to our velocity, and our velocity accumulates over time.
Since we are simulating integral, which is continuous, but with discrete data from Prometheus, it turns out that the Prometheus formulas actually do all the discrete math that is the sum of the integral of sums approximation. So Prometheus is doing all the work for us fairly naturally. You notice the formulas are very straightforward.
Cool. And last but not least, the delta V, the change in our velocity, is simply that math, those three terms added up. For simple reasons of we don't want to have it go insane, we clamp it to, between a certain set of values. So technologies used in this demonstration should be familiar to everyone. We're obviously using Prometheus, which is a time series database. We're using Grafana to visualize. And I've built a simple Go binary that serves as the controller that sets our set point as well as the three coefficients that we're using. So it's all running on a Kubernetes cluster. And at this point, we'll sort of get into a demo. So here is this.
So, and I think it's worthwhile to mention here, so it's useful to have a demo rather than trying all this math out on a production cluster or a staging cluster. Doing this here, so tuning a PID controller can be quite difficult, and as it diverges, you can end up with a lot of strange values happening on your cluster, so you don't want to do that. So by building a simulation and working through it gives you an opportunity to figure out what's actually going on with your system, because the numbers are going to be very different depending on the size and scope and scale of your system versus it. So it's really good to have a test bed where you can play with it just in the abstract before you start applying it to real stuff. So that's what we've got here.
All right. So let's talk about the components of this demo. Up at the top here, we have our current location and our current set point. Down here, we measure the velocity as well as the change in the velocity. And this part over here is where you can see the delta V terms. So I have quieted our system. There's no longer a set point. It's just set to 0. All of the values are 0. Using only a proportionate controller, so this value, this KP value of 0.5, we can set our set point to some value, and we will see on the screen in a second. So first the set point moves up.
Yay.
And eventually.
So the cluster, the Prometheus, is actually sampling at every second, and then we're redisplaying every 5 seconds. And of course, well, we'll do a reset here because it's not actually
it's not
pulling
cooperating.
out. Yes. Tested this 16 times this morning, and the 17th time we get this.
I think I forgot to reset the reset.
Well, let's go. Let's dig into it. Burn it down and start from scratch.
No, let's actually. Oh, is that right? Or was it not so right? Why is it not so right?
It's not finding the.
There we go. Okay, so now we can see that the delta V has gone up. Delta V has gone up, and our purely proportional controller moves our location up and overshoots, and moves our location up and overshoots. And it will continue to oscillate at roughly the same point around our set point forever. This is what a purely proportional controller will do. It will get there, and then it will overshoot. So by adding in an integral and derivative proportion, let's zoom in a little closer because it's still showing some other data here. Oh. Yeah, there we go.
So now you can begin to see the 3 different terms diverge. So the P, the I, and the D are diverging. And did it?
That's a little weird.
Yep. Well, that's why we have a clamp. Because it's way off. It should only be in the range of say, around 10 to 20, and it's up around 400, which is not expected. Okay, so now it's coming back down.
Okay. So now we've adjusted the D term to overshoot less. And
so that's similar to when you're steering a ship, before you actually get to the direction that you want to head, you're going to go ahead and start turning the steering wheel back because you know the ship is still going to have angular momentum that's going to keep it heading and keep it turning while you ease off on the steering. So that's what the D term is all about, is sort of stopping that tune sooner than the metrics and the eyeball tells you on course.
right. And so now that we have adjusted our terms so that we actually have a working PID controller, you can see that it is slowly converging. Each of these humps, each successive hump, is closer to our set point value. So let's give this another minute or so to converge, and then we can try adjusting the set point. Given enough time, a PID controller will get to an arbitrarily small error. However, it will never actually reach 0. You will always see it continue to oscillate a little bit above and a little bit below. Most places that is nothing compared to the actual error from the measurement of the system and from the change in your set point. Your set point will change more often than you can pull the error out of the system. So having converged mostly, let's set this set point up to just another value. So you can see that the 3 terms here will start to change as soon as it actually picks it up. Okay, so our set point has adjusted.
The set point's the yellow line, and the process variable, the actual variable that we're trying to create in the system, is the green line.
Yeah. The proportionate portion of our, as well as our overall delta V, went up in response to that, and then the derivative term pulled it back down to prevent overshoot. And as it moves in, it is still homing in slowly. So we can continue to do that. We can continue to adjust the set point and adjust the terms that we use, the coefficients, to hone in on what our system actually wants and the desired scaling effects. Certain coefficients will give you more or less overshoot or undershoot. As you can see here, it is currently undershooting by a bit, but the integral term will eventually catch up with that and reduce our error. So let's go back to our slides and talk about tuning methods. So there is an algorithm, and there are several algorithms for tuning it, but at its most basic, you can hand tune. You can take your proportionate value, you can take your integral value, and you can take your derivative value, and you can start off by tweaking them probably in that order. Your proportionate value is your most obvious, direct correlation to your system. There's also several specific tunings of PID controllers. The Ziegler-Nichols method is one of them. And using that method, you start off by tweaking your proportionate value until you get a steady oscillation. Keep going until you get until you find out the maximum p-value that you can use to get a steady oscillation as opposed to an oscillation that diverges. And then measure the distance between 2 peaks of that steady oscillation, which will give you the time of your oscillation. Using the time, you can plug it into a formula, and the Ziegler-Nichols method will just give you I and D values for your p-value. The other thing you can do is you can damp. Using that same method or using your existing tunings, cutting all of your coefficients in half will dampen your PID controller. It will move slower, and thus it will overshoot less. However, that comes with a corresponding increase in the amount of time that it takes to actually finally converge.
Yep. So about this talk, our slides are on a GitLab repository along with all of the Grafana and Prometheus code for this and the controller. The talk piece is available at that URL. And I think we've got, there are a few other places that we want to continue to look for. We want to make sure that the repository has got better explanations about what's going on. It links to the Wikipedia article and the other mathematics behind this. And build, so we had planned to build an actual Kubernetes model and have a couple of pods running, but we wanted
Doesn't work.
Yeah, you got to get the basic math right first. So that's further work. We'll be building that out in the repository, so you can check for changes on that. At this point, we're open for questions.
Yep.
I have a question about the type of the type of action that you can perform with a PID controller. So, looking from that, it looks like the action that it can take has to be somewhat continuous. What happens if you are dealing with a non-continuous system or with a discrete system where the action can only be like defined by an integer or something like that? So,
a PID controller is designed to operate in steps. It is an iterative system. In our demo, it is actually a discrete system. It is just discrete at a rate of 1 second. In a real working system, you would probably go much slower than that if you were driving a Kubernetes cluster, for example, or much faster than that if you were driving an airliner or your car's cruise control. So it will work regardless of how discrete your system is, but it will take much longer to converge according to how often you iterate.
So I'm talking about the variables in the system. Like in the case here, you're dealing with velocity and location as the variables, and those are essentially continuous variables. But if you're dealing with a Kubernetes cluster with, let's assume it's not relatively big, then you're dealing with mostly a discrete problem.
Right, but the number of pods you're running is discrete, but to some extent you can round it. Those continuous values will round, and if you have you'll get close enough, your error value occasionally cause your integral component to grow, and it will kick you up to another pod for a while, and then it will go down and it will kick you down to another. It will always be metastable around 1 or 2 pods.
Right, and if it's oscillating between discrete values inside the bandwidth of a discrete value, right, it's not going to actually change. So that's how a lot of other systems run, is they oscillate at a level that's well below opening and closing gates in some kind of feedback loop, or the level of perceptivity. If it's steering a ship, nobody's going to notice that it's moving back and forth by hundredths of a degree.
Very frequently, PID controller is also used for heating elements, which operate in a discrete fashion. They're either on or they're off, and there is some threshold value that they turn on. Basically just a 0 or 1.
Yeah. Question in the back here?
Many years ago, we tried to build something like this. It didn't work terribly well. The system itself was early versions of the Google file system that had really terrible rate limiting. So what we tried to build was a governor that would notice when the system was in overload, notice, well, who's the busiest user on it, and rate limit them. And then slowly increase or decrease the rate limit until the system came back to happiness, basically. It was intended only for short term. It was tricky. And the biggest problem was, well, it was a distributed system. We were thousands of nodes. So we were reading in the rate. We were setting the rate on thousands of nodes, but also the load maybe or latency on thousands of nodes. well do PID controllers work when you have multiple sensors rather than one?
The resolution is much harder to get right when you have multiple sensors. If you have it does rely on the assumption that you have a relatively uniform output value. It only has one, process variable that is measured. You could run PID controllers for each discrete operation you have, or you can assume that that the average or the P95 latency of your operations is the correct one, the one that you're targeting. So no, you have to boil it down to one process variable for a PID controller, and if you have discrete components, a single PID controller will not fully express that.
All right. Well, thank you very much. Please thank Ted and Mark for their presentation.
Thank you.